So I think one of the big things that I might have not quite hit home enough yesterday, when we draw these pictures, these dot diagrams, and you're figuring out if it's a single bond, a double bond, a triple bond, you need to make sure your end product has no lone electrons. So a lone electron would be like that. Here's your lone electron. That's not okay. The second thing that you need to make sure is followed is that all elements satisfy the octet rule. However, hydrogen will still only have 2 electrons. And the third thing, and it probably should really be the first thing, is that your drawing matches the formula. And what I mean by that is I have been getting, like, if the formula was something like this, I would have people giving me 4 carbon atoms since it has 4 valence electrons. So you need to make sure that if your formula says you have 1 carbon atom, your drawing has 1 carbon atom and the 4 hydrogens. Does that make sense? Okay. So now this section or this part of 9.1 pretty much breaks all those rules. These are the exceptions to the rules. So the first exception is called a coordinate covalent bond. And this is when one of the atoms in the bond is going to contribute both of the electrons in the shared pair. So usually when you bond something together, so like the carbon and hydrogen example from the first page, carbon contributes an electron, and so does hydrogen to each of these bonds. But sometimes that just doesn't work. And the example here is carbon monoxide. So that's 1 carbon and 1 oxygen atom. And so if we do it this way, where 1 atom contributes an electron to each of the bonds, you get this diagram. What is wrong with this diagram? Marta? Okay, so the first thing that's wrong is carbon only has 6 electrons on it. What's the other thing that is incorrect? Zoe? Pardon? Yeah, there's 2 lone electrons. Right here and here. So those are both bad things. So a coordinate covalent bond is when we take this pair of electrons from oxygen and use it to form the triple bond, so that way we can satisfy the octet rule on the carbon atom. So now carbon down here exhibits 2, 4, 6, 7, 8 electrons, and the octet rule is satisfied. Same way when we count back on the oxygen, it has 2, 4, 6, 7, 8 electrons. So the octet rule is satisfied, check. There are no lone electrons, check. And our diagram follows the chemical formula. Does that make sense? Yes? Okay. Polyatomic ions. Polyatomic ions, we know, are a group of covalently bonded atoms, and they also have a charge that it's used in ionic bonds. And so when we draw the structure, we put it in a bracket and we write the charge outside of it as a superscript. So you pretty much draw them the same way, but you have to factor in more electrons than the valence electrons tell you to, or fewer electrons. So we'll kind of work this problem backwards to show you what I mean. So how many valence electrons is nitrogen going to contribute to this? 5 valence electrons. And since there's only one nitrogen atom, it's still 5. We don't have to multiply. How many will hydrogen contribute? 4, because there's 4 hydrogens and there's 1 valence electron on each for 4 valence electrons. So, as is, there should be 9 valence electrons in the drawing. But if you notice, there's only 1, 2, 3, 4, 5, 6, 7, 8. Why is that? Daniela?
Because of the plus 1 charge, which means you have to subtract 1 electron.
Very good. Since it has the plus 1 charge, that means you're short 1 electron. So we have to subtract that from our overall count, and we end up with 8 valence electrons. Which now, does that match in our diagram? Yes. So again, notice we've satisfied the octet rule. In hydrogen, it's 2. There are no randomly placed electrons. They all have a home and they all have a partner. And it matches with the formula, which would be technically NH4+. So remember, with the polyatomics, the brackets and the superscripts are a must. Okay? So let's practice. Here we have sulfate we're going to practice with. And sulfate is SO4 minus 2, or 2 minus. So we first need to figure out how many total electrons need to be in our drawing. So for sulfur has how many valence electrons? 6. Do we need to multiply it by anything? No. Nope. And then oxygen has how many valence electrons? 6. Okay. And do we need to multiply that by anything? 4. Why are we multiplying it by 4? There's 4 oxygens. Very good. So here, the 6 plus this 4, we should have a total of how many electrons? 30. And now we need to take into account the charge, this -2. Does that mean we add 2 electrons onto our count or remove 2? You add the 2. So we add 2, thank you. So now for this drawing, we need 32 electrons. That is our goal. Okay? So let's start with sulfur. Sulfur, we said, has 6. So 1, 2, 3, 4, 5, and 6. Okay. Place the oxygens. This one happens to work out, but it doesn't work out very nicely for learning purposes. So if we put and satisfy the octet rule, if you just count the electrons, the total electrons on each of these, and add them up, you will see that they come out to the 32 electrons. Put the bracket around it, and we throw our -2 up front. All right, anyways, it's me and my color coding that's not working out. It's not a big deal. It's just me being hyper anal. There has been questions about how to know which element you kind of start with. And so generally speaking, there are exceptions to this, but generally speaking, you take the less electronegative element and put it in the center, or start with. So generally, carbon and sulfur will almost always be central atoms. Nitrogen might be another good one there. That might help with the rest of our assignment today. All right. So sometimes in this, you might notice that you can, or a double bond or a triple bond could be in multiple places. So this is what we call resonance. Resonance is the use of one or more Lewis structures to represent a covalent bonding in a molecule. So an example here is ozone. Ozone can either be drawn with the double bond on the left side or on the right side. There's no rules that tell you where that double bond, between which O's that double bond needs to be, because both of these structures are true diagrams. They're both true. So the true structure of the molecule that displays resonance is an average or a hybrid of these resonance structures. So we can't really draw a hybrid of these structures. So we indicate with this double-headed arrow that the real structure is somewhere in between the 2 or the 3, sometimes even 4 possibilities. Okay? Many polyatomics will demonstrate resonance. So here, how do we know that it's a polyatomic, first of all? There's the brackets and the charge. Good. And so how do we know that it's a resonance structure? The arrows, and if you look deeper within the drawing, what do you notice? Yeah, the double bond is in different places in each of these. A resonance structure will only show up if there are double or triple bonds in the diagram. That's the only time you need to worry about a resonance structure. So here are the 3 exceptions, Studi, to the octet rule. They're kind of important. Okay? The first exception is called an incomplete octet, and it's exactly how it sounds, is we're not going to get 8 electrons. The second is called the odd electron molecules, and then the last one is the expanded octet, meaning that they can hold more than 8 electrons. So, incomplete octets, generally happen with beryllium, boron, and aluminum. So these ones are pretty much, you just need to memorize which elements are the exceptions. So beryllium is an alkaline earth metal, and it makes covalent bonds. It's a metal, but it makes covalent bonds. This is because it's very small, and it has a very high ionization energy, so that means it would take a lot of energy to remove any of its valence electrons. It has 2 valence electrons, and it cannot achieve a full octet. So here, if we're making beryllium hydride, there's just not enough electrons available to make beryllium hydride. So beryllium is satisfied only having 4 instead of a complete octet. Again, these are just elements that you're going to have to memorize that do not follow the octet rule. Boron and aluminum also will not achieve a full octet. Both of these have 3 valence electrons, and so they will only have the 3 available for bonding. You're not going to get 8 out of them. They're just literally not there. There's no way to pull in any extra more. There's no space. The odd electron molecules, this is where the total number of valence electrons is odd. So remember when I said you can't have a lone electron? This breaks that rule. The total number of valence electron is odds. It is not possible for all atoms to achieve an octet. Nitrogen-containing elements are usually part of this exception. So anytime you're drawing a structure for nitrogen, you need to double check if there's enough electrons. More so it's going to be nitrogen doesn't have all 8 of them, and that's okay. It generally will just have 7. And so we indicate that with showing the 1 electron and then putting a plus sign above it. Expanded octets, for some nerdy reason, these are my favorite, maybe because they're the most obvious to see. Some electrons can hold more than 8 valence electrons. Pretty much if the element is in the 3rd period or higher, so the 3rd row on the periodic table, the 4th row, the 5th row, those elements are likely to expand their octet, meaning they can hold more than 8 valence electrons. This is because the D sublevel becomes available to make extra bonds and hold more electrons. Phosphorus and sulfur are 2 elements that react with halogens to make stable compounds in which the central atom has an expanded octet. Xenon is another big one that will expand its octet, which is really kind of crazy because xenon is a noble gas, so why is it doing any reacting? And really the answer is because it can expand its octet. Bond energy, this is the energy required to break a covalent bond between atoms. If you have a high bond energy, you have a really strong bond. It's a very stable molecule. It's not likely to break. Halogens will all naturally occur as diatomic molecules. That means they're bonded to themselves. And it takes a relatively small amount of energy to break these bonds. So this chart gives you the diatomic molecules and how they're bonded. Notice that nitrogen, when it bonds to itself, will form a triple bond. And then it also kind of makes sense if you look at it that it has a very high bond energy. A triple bond is very strong compared to a single bond. Carbon here can also form the triple bond to itself, and that bond energy is also really high.